real quick review, something that we're going to be doing a lot of today. Actually, well, first off, we talked about this before. There was the change of base formula that if you have log A of some number and you don't have, say, a log A key, you could change this. And we went over this in painstaking detail. So I'm just going to write this on the board, that log B of X divided by log B of A is how you compute such a thing. So you're going to have a few of these in your homework. For instance, one of them will say to compute log base 5 of 0.78. And it's going to tell you to use log base 10 to do this. Don't use log base 10, use natural log, and you're going to get the same answer. But just always get in the habit of using natural log. And so the way we would compute this is to say, okay, I'm kind of thinking about this change of base formula. It says I have a log of something I don't want. I want to turn it into a log of something I do want. Log of any base, well, how about the natural log? So we use natural log. And so we do that. And then we say, okay, which one goes where? Well, the input to the old one goes on top here. Okay, so 0.78. And we divide by the log of whatever the old base is right there. And so you'll have like 3 of those in your homework. Quick review. That's what you need to do for those guys. And again, the book will say to use log base 10. And you could, and I'll never know. But I recommend using natural log all the time. So unless in the special cases of, like, remember pH, how it's defined by using log 10, or the Richter scale or the decibel scale, they're defined in terms of log 10, then you want to use the common log base 10. In all other cases, use natural log. It's much better, for reasons that we can't really get into. So, all right, there's that. One more thing, okay, and because we are going to use this extensively today, so I want to be very clear about a couple things. So I've written this 1,000 times. I'm going to write it again. A to the log base A of any number is whatever that number is, provided that X is a positive number. Because you can't put, well, you can put a negative number into log, but we're not doing that in this class. And so we're going to say as long as X is a positive number bigger than 0, then that always works. On the other hand, if you take log base A of A to any number, and this could be 0, this time X could be 0, X could be negative, X could be positive, any real number, X, that's going to work. And it's going to come right back. Since that's true, I want to be very explicit about this because we're going to be using this a lot. That, well, that's log base A, and we're taking the exponential of A. So by analogy then, if we do e to the natural log of X, that is the thing that gives you back X. Similarly, the natural log of e to any number X is the thing that gives you back X. All right, this just comes from the definitions of exponentials and logs, and the natural log happens to be base E by definition. And so we are going to be using especially this one a lot today. It's going to be our new best friend. And in the past, the way that we've used natural log has been if we had, say, something like this. We have like 7 to the X equals 3. And so we took the natural log of both sides. The reason we did that was so that the X could drop down, so that we could isolate the X, get the X by himself. And then finally do something like this. Let me know when you have all of this written down right here.
Okay.
Okay, so what it's going to be, we're still going to be using natural log, only the thing is that the base is going to be e. And so we're going to have equations like this, where we have, say, e, and let's just go to the 2x just to make things a little bit interesting. We'll say we're going to have equations like this. And now we're going to say the same game, right? It's like x is locked up in an exponent and I need to get it out. So I'm going to take the natural log of both sides. Only now, since the base is e, well, it just makes my life slightly simpler, because it's like, well, you just undid what you did. You took a number, multiplied it by 2, and then put it up into e. And now you're just saying undo that right here. And so we'll just undo that. This is the same thing as just 2x. By that first nifty fact I wrote up on the board right there. Yeah, that's Kayla, buddy. Now, real quick, yeah, this is just an aside. I just want you to watch this. This is the same thing as doing this. Watch, like if I'd had this right here and said, well, by analogy over here, whatever's in the numerator drops out, I could just say, well, that's the same thing as 2x natural log of e. The natural log of e is equal to 1. Let's think about that real quick. If e to the x, and you plug in a 1, you get e to the 1 is the output, or just plain old e. And therefore, if you take the natural log of it, it comes back to give you the original input. That's what logarithm means, right? You have some output from an exponential, you find out where it came from, that's what the log is. And so when you take log of e like that, you're just saying, well, you plug some number into e to the x and you got out at e to the 1. Oh, I guess it came from 1. So this entire thing is just equal to 1. 2x times 1 is indeed 2x. So even what I'm saying here, and the reason I'm going into this is, even if you just go on autopilot because you've been so used to doing this and you pull out that, blah, 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 you'll still end up with this right here, as long as you recognize, oh yeah, the natural log of e is just 1. And so there you go. So does that make sense what I was saying? You got that?
Yeah.
Okay. So long story short, this is what we're going to be doing today. We're going to have a lot of this type of stuff, something up in the exponent. And since it's base e, we just take the natural log, it brings it back. And so now to solve for x, I'm going to just divide both sides by 2. And we're going to be seeing this type of thing a lot today, this type of flow. And so we want to be ready for that. Okay, any questions before we get into our actual applications for today?
I don't think so.
Okay, so that change of base thing, we already talked about it. We are not going to get into it. And so we are going to talk about a few different applications of the exponential function. The exponential function. You say, aren't there a lot of them? Well, no, it's really E is all that you need. In the same way I said that before, like you only really need one logarithm, and it's the natural logarithm. In the same way, you really only need one exponential function, and that is e to the x, or e to some power. At any rate, we're not really going to go into that. So we talked before that this function, the exponential function, is a really great way to model real world phenomenon. In particular, one thing we said is population. And in general, we're going to think about this as the population of something as a function of time can be modeled by this formula. The initial population, that little sub-zero is, we usually think about that as the initial, whatever initial is. Maybe we're starting in 1970. Maybe that's what we're calling initial. Or maybe we're talking about when I hit the clock, or when I'm in the lab and I have a Petri dish and I take some bacteria and put it in the Petri dish at a given time. That would be time 0. And however many bacteria I put in the Petri dish would be my initial population right there. Then we take that and multiply it by e raised to the k times t, where t is time in some units. Maybe it's years, maybe it's months, maybe it's seconds. Depends on the context of the problem. And k is some constant. What we're going to be doing today is pretty much all day, we're just going to be solving for k, because the idea is we're going to have a bunch of different scenarios and stuff like that. And we're going to say, we want to model this scenario with this function right here. And usually the initial population will be easy to find. Sometimes it won't be, but we're going to get into ways that you could kind of hack the system and make it easy for you. But the bread and butter comes down to finding whatever k is, as we're going to see. So, okay. All right. Here is number 22 from page 555. Ooh, I like that triple nickel. Page 555, number 22. And it says, the approximate population of Dallas was, so we're going to say population of a place was 680,000. Yes, 680,000 in 1960. Okay. Then it says in 1980, it was 905,000. Okay. It says find k in the growth formula. These are all like this. It'll say find k in the growth formula. I would like it if you just give me the final thing, just like when we were doing lines, basically, right? When we're doing lines and we had a question that said find the slope or find the y-intercept, I'm like, just write down the equation of the line. Just let me see the equation of the line or the function, right? That's what I'm going to be asking for each one of these. When it says to find k, what I want is, in the end, I just want to see this thing where you've actually solved for your two unknowns. And this is something I really want to stress here real quick, is this thing is a relationship between x and, we can think about it as x and y, right? Or input and output. And so real quick, when we had y equals mx plus b, when that was our general form of a line, we had, this is always going to be x, right? Because these are my inputs. This is always going to be y because those are my outputs. And so we had some equation, and there were basically, what this came down to, there were two unknowns. There were two unknown constants. The m is my one unknown constant, and the b is the other unknown constant. And the idea was if I could find 2 points, then I could do some magic and solve for this constant, solve for that constant. And what I always wanted was in the end, you give me what those constants are by writing the final formula like that. This is going to be very similar in that you have some output P, which is always going to be some output. You have some initial constant, something here, something here. So in other words, the T's are always inputs. And so just like with this, in the final thing that you're trying to find, right? You know that X needs to show up there. In the final thing you're trying to find, you know that Y needs to show up there. The same kind of things going on here. The final bit that you need should have the letter T right there. And since these are outputs, your final thing needs to have either P or whatever variable you want to use for it. But that's the idea, is that that is the output. And so it's not a specific number. But these things are specific constants. These are constants. And those constants we need to find. And you'll notice that this is going to be very similar. In order to find, this goes back to like one of the first things we ever talked about. In order to determine 2 unknowns, because that's what we had here, right? That X is always X, Y is always Y. And we really, when we're trying to find the formula for a line, we have 2 unknowns, right? The M, we don't know what it is, and the B, we don't know what it is. And in general, we needed 2 equations to find 2 unknowns, or 2 bits of data. We could think about that, because if we know that the slope was 2, we could think about that as, okay, well then one equation is that n equals 2, and you could think about that as an equation or whatever. Another thing, another way of thinking about this is, and this is how I always recommended doing the lines, is that if you have 2 points on a plane, and you say that the line goes through those 2 points, well, that's technically 2 equations, because this says that when your input is this, your output is this, right? And so we had some kind of input-output relationship. Ditto right here. We knew that when your input was this, your output was this. And so we were able to plug in the input here, plug in the output there, and then do some kind of magic to solve for stuff here. The same exact thing is true here. We have 2 unknowns, right? Because what you're going to be trying to find pretty much in every single one of these that we do is you're trying to model some real world data with this function. This function has an input T, an output, whatever that stuff is. And then it comes down to finding whatever these 2 unknowns are, your constant K and your constant P0. And in the same way, 2 unknowns, we're going to need 2 equations. Or we could think about that as 2 data points, because that will give us 2 equations. And so this is how we're going to do it. So, okay, I'm going to get rid of this stuff here. Can I get rid of this stuff here?
Yep.
Okay. So population was this, in that it was that, and we want to know, find K in the growth formula. Rather, we're going to say, find the general function. And use that to estimate the population in 2015. Okay, what I'm going to recommend you do with every single one of these is the same thing that I recommend that you do when you have lines, and that's to draw it out. And so Now we're going to talk about this because the naive way that we're going to do this is not the best way of doing it. And I want to go through the naive way, and then we're going to go through the better way, and you'll see what I'm talking about. So here we go. We have a relationship of inputs and outputs, and we know that time is the input. One, because I mean, we're anticipating this, right? But time is almost always the input. So what I'm going to do is graph this out naively and say, okay, I have a t-axis is my input axis, and my y-axis is my output axis, or my p-axis. I could think about it that way. Now this says that in 1960, okay, so I'm going to think, okay, here's one point coming up. In 1960, so 1960 is the input, the output is 680,000. And so I'm just going to draw a dot right here and label it. And we don't have to use thousands. We could think about this in thousands. And so rather than writing 680,000, I'm just going to say, how about 680? And we'll know that we'll just keep it in our mind that, okay, we're talking about in thousands here. And so when I see 680, I know that that means 680,000. That's pretty standard, right? And then this says that when the input is 1980, so I'm going to draw again, 1980. Then the output was, well, one, to notice it's bigger. And so I'm going to draw it higher up. It says the output is 905. 905. And so now what I'm going to do is just think, okay, I'm modeling this with an exponential function. All exponentials either look like this or they'll look like this. And since this one's getting bigger as we go to the right, it's got to do this type of thing. And so I'm just going to go ahead and draw a curve connecting these guys like that. There we go. Okay. Now, here comes the hard part. Well, actually, well, the hard part's coming up in a minute. Right now, this is actually the easy part because I know I have two unknowns. In order to solve for two unknowns, I need two equations. And I also know that one data point is the same thing as an equation because here's my equation that I'm trying to fit. And it says that when I plug in a 1960 in for t, then the output here is going to be 680. So I'm just going to take that point and plug it in, right? We're going to say, okay, you have some initial P0, e to the k, we don't know what it is, but then k times 1960, just like that. Not using my brain here, I'm just saying, well, this thing means that you plug in a 1960 for t, then your output is 680. Easy enough, okay? And not use my brain yet. The second equation that I'm going to get is going to be when I plug in a 1980, I should get out a 905. So 905 is my output when I plug in a 1980. So I have P0. E to the K times 1980.
Oh, I wrote that wrong. Neat.
Let me know when you got this stuff.
Okay.
Okay, now I said a minute ago that what we're doing right now is the naive way or the hard way of doing this. And I really want to go through this because we're gonna in a minute do it again, but with this nifty little hack that will make our lives so much easier. But I really want you to pay attention to this way of doing it because you will not always be able to use the little hack that I'm about to teach you. Sometimes you have to do what I'm about to do, especially if they, well, I'll go into especiallys after I do both ways. But right now, this is what we got. And it's like, okay, the idea, as with anything, is to somehow get one of these variables by itself. And there are a bunch of different ways of doing this. The easiest way, and the way that I'm going to recommend to do this, is what I'm going to do is take one of these equations and divide it by the other. I'm just not going to go into this yet. I'm just going to take, in fact, and I like to take the bigger thing, the bigger output, and divide it by the smaller output. And so I'm going to take this right here and divide both sides, or rather not both sides. I'm going to say, well, then let's divide this side by 680. And I'm going to divide this side by that guy right there. 1960, just like that. Why? Well, the idea is if I could get rid of one of my constants, if I get rid of one of my unknowns, then I could isolate the other one. And this particular type of function lends itself to that really easily, because as you can see, whatever this number is, P0 divided by P0 is gone. That's nice. And so now I have 905 over 680 on the left-hand side is equal to e to the k times 1980 over e to the k times 1960. Right? So like, for instance, if P0 happened to be 10, we would have 10 times some number divided by 10 times some number. We could just cancel out those 10s. Another thing to notice is I went ahead and simplified up here when I first wrote these numbers down. I said, well, how about instead of writing 680,000, we'll just think in terms of thousands and stuff. Had I not done that, had I written the entire thing out, at this point, I would have ended up with 905,000 divided by 680,000. And I'd say, oh, hey, look, I could simplify that a lot. For every one zero, I could cancel out another zero, and I would end up with 905 over 680. And so, whatever, like, that's just the point I'm making. Okay, so now what do we do? Trying to get the k by itself. And so here's just real quick before we go into that. I would like you to figure this one out. What's 2 to the 5 over 2 to the 3?
Oh, sorry.
2 to the 5 divided by 2 to the 3.
4.
Yes, but yeah.
Oh, 2 to the 5 minus 3, right?
Yeah. Actually, you beat me too. I was just gonna say it's 2 to the 2. But yeah, but how did we get that, right? You have 5 of them on top, 3 of them on bottom. You know they're gonna cancel out. And so you say, yeah, you're right. 5 minus 3 right there. You take whatever's in the exponent of the top thing, minus off whatever's in the exponent of the bottom thing. And so I'm just going to do that right here. I'm going to say, wait a minute, you have e raised to some power divided by e raised to some power. I could simplify that by getting it all together and saying, okay, e to the top stuff minus the bottom stuff. So we have k, you really are up there, 1980 minus k times 1960, right there. You really are up there. And so I still haven't really used my brain. I just said, okay, I'm just going to move some symbols around here. But now I got to start thinking, okay, I'm trying to isolate K. That's the whole point, right? I'm trying to get K by itself so that I could get some expression for K. And so can I factor out a K from that expression?
Really high.
Oh,
What am I left with if I factor out a K?
1980
There you go.
minus 1960.
Yeah, which is what? What is 1980 minus 1960?
20.
It's
Is that
what?
right? 1980 minus 1960. 20.
20. I thought you said 40. But there you go. 20, right? So K times 20. There you go. All right. So now remember what I said at the beginning? Like we're gonna be doing something a lot this class where we're gonna take the natural log of both sides. Why? Well, because the thing I'm trying to get by itself, in this case, K, is locked up in an exponent. And so we need to undo that by taking a log of both sides. And it just turns out to be that our favorite log is the thing that exactly undoes this. So to be explicit, what I'm about to do, I'm going to take the log of both sides. So I get the natural log of 905 divided by 680 is equal to the natural log of e to some stuff. And that's what makes the stuff pop out. So I'm going to just write this above. Actually, let's finish it over here. I do want some more room. So on the left-hand side, we have the natural log of 905 over 680.
Oh boy, oh boy, oh boy, oh boy.
80 equals, well, log of e to anything is just whatever that anything is. That's why I chose to take a log at this point, was to make that stuff pop out. And so now I just have K times 20 on the right-hand side. The whole name of the game was get K by itself. It's almost by itself. How do I finally get K by itself here?
Did it. You did it.
Good job, buddy.
And then I really up here.
Hold on, wait.
Okay.
Okay, you got K to the K times 20 because the natural log of E is equal to 1, right?
Yeah. There you go. That's another way of thinking about it, right? Like I was saying earlier, you could say, well, hold up. Natural log of e to anything is just whatever the anything is. Or if we don't trust that, we could say, well, the natural log of e to something is you pull that something down like that. And then say, well, the natural log of e is e to the 1 is just 1. And so we say, yeah, that's the same thing as that. Or we could think about it as recognizing that these are inverse functions of each other. E to something does something, and then you take the log, just brings you back to where you started, which means you plug in an x into the e, into the exponential function, and then you take a log, it just brings you right back to where you started. So either way you want to think about that, they're both equivalent. They both work. And so K equals what?
You just divide by 20.
Just divide by 20. It's that simple. I say it's that simple. It looks messy. It looks really messy. But what we end up with is some number, log of some stuff, whatever that comes out to. We can plug that into a calculator and find it out. Then we take that and divide it by 20. And that's what my K is. Right there. Okay, so we have one variable. We have one constant. One of our unknowns we have solved for. At this point, I'm going to go ahead and write that the same way as when we were working with lines, and what I recommended to do was that we write this somewhere on our page. And then once we've found M, we say, oh, M equals 2. Well, I'm going to go back up here to the top and write 2x plus b. I'm going to do the same thing at this point and go back and say, okay, since I know that k equals that, I'm going to plug my k back into this thing here and say, okay, the thing that I'm working with is p equals some initial value p0. E to the, instead of k, I just have that number, which is log 905 over 680 all over 20 times t. Now, I know you're a fan of writing your division like as though, because apparently you really want to save the trees, like you love the trees and you hate using paper and you're trying to fit everything on one line.
That's because unorganization, like it bothers my head so much because it's so unorganized to like have numbers everywhere to me.
Yeah,
but I will do it. I will learn.
Life's going to be a lot easier if you take a little bit of vertical space here, which I didn't up here. I tried to cram it in, and I'm guilty of doing what I'm accusing you of doing. But I'm just saying, you do it however you want. Like, and if I'm grading stuff that looks like this, 905 over 680 over 20 times t. What do you mean by that? Please use parentheses if you're going to do that. Although that would look a lot better. We could use space. We found k, so we plugged it back into our general form of the equation. And now we could use either of the data points that we have to find our remaining constant that we don't know. Because remember, in the back of our head, we're thinking the p out here is always going to be p. The t is always going to be t. So the only thing I don't know is what is p0. And okay, well, I have one unknown. I only need one equation, and I could use any one of them to find that out. I guess I'll use the smaller one. It doesn't matter. You can use either one, and we'll get, well, it won't look the same, but it will be the same answer. So, okay, what I'm going to do is take this equation, plug in a 1960, and I'm going to get out a 680. So 680 equals P0 e to the natural log of 905 over 680 all over 20 times t is 1960. What I'm going to do right now, just to make myself a little bit more sane, is to just clean this up a little bit. And like I've said before, when we have numbers, I like to write them out in front of log, the same way I like to write numbers out in front of a square root. So that's what I'm going to do right now. I'm going to take that 1960 over 20 and just write it out in the front of the log to get P0 equals 1960 over 20 times natural log of 905 over 680. Right.
1860. Okay.
And now,
Hold up.
well,
Wait.
Wait, did you say wait?
What did you do? Sorry, I'm still.
Okay, so I plugged in the 1960 here, yeah?
Uh-huh.
And then I said, well, this is some number, let's call it A, divided by some number, call it B, times some number, call it C. I just said, well, I'm going to rewrite it as C over B times A. Why? Because I want that thing that's up there on the right-hand side, because it looks a little bit better. It's just aesthetics here. That's all I did. And so I wrote the 1960 together, but just stuck it out front right there. So there you go. Okay, now this is, and I'm gonna copy this again. You don't have to copy this again. But what I just said is that 680 equals P0 times e to a bunch of numbers. 1960 over 20 times the natural log of 905 over 680. Okay, now, wait a second. I could, if I were so inclined, I could plug this into a calculator right now. And I could find whatever this is. E to a bunch of junk is gonna give me some number. So what I'm gonna do is just think about this as some number. So I have some number times the thing I'm trying to solve for equals some other number. Why don't I just divide both sides by that? And I get that P0 is equal to 680 divided by all that junk, which looks really ugly. And we'll take care of that. 1960 over 20 times log of 905 over 680. That is equal to P0. So I found now the two constants that I needed to find. It looks horrible. I get that, and I'm sorry. It looks horrible, but this is an exact answer. That's what's really nice about this. Right? We didn't like plug this into our calculator and round something off and then end up with something that, and especially when you're working with logs and exponents, rounding is your worst nightmare. You're going to end up with something that's not nice at all. And so I'm going to recommend that you actually do it this way. Well, you'll see in a minute, like I told you, there's a hack to make our lives a little bit easier in this case, and you'll see how much nicer this is going to be in just a second. But, and again, I wanted to mention that sometimes you can't get away from it. Sometimes you have to do all of this junk. And really, this right here that we just ended up with is a worst case scenario. Like, you know, like it's not going to get really any uglier than this. If you have this thing that you're trying to model to two data points, really, this is as ugly as it's ever going to get. And so I want to get this final result here. And so what I'm going to do is take this number for P, 0, and plug it in finally to our equation and say, okay, then the thing that Justin is making me write down, even though all they asked for was K, is this. P of T equals P0. Well, that's P0. Ugly. Okay, 680 over E to all that stuff. So 1960 over 20 times the natural log of 905 over 680. That's my P0. I just plugged it in. E to the KT. K is natural log of 905 over 680 all over 20 times T. I'm not a fan of writing my T out on the right-hand side of a log, but just because this is what's in our heads right here, that this is the original thing, and the T shows up on the far right, I'm gonna leave it like that because, okay, it's okay.
Ice cream, ice cream. Ice cream.
We don't have any ice cream, buddy. All gone. I'm sorry. Okay, so let me know when you have that written down. And we're about to make our lives a lot easier.
Oh, leave it alone. Leave it alone. Leave it alone. Leave it
Yeah.
alone. You will not leave it.
I hate it like that.
I will really up here.
Yeah, buddy. Excuse me.
Okay.
Okay, so that was really bad. And like I said, that's a worst case scenario right there. What we're going to do is use our brains a little bit and say, okay, back to the very original equation. And or the original prompt, right? And notice we haven't bothered to do this yet. We could have estimated the population in 2015 by plugging in a 2015 right here and plugging all that into our calculator, and we'd get some amount in 2015 that would finalize what they're asking for now. But in this case, what I'm doing is this. I'm given this prompt and I say, okay, in 1960 it was this, in 1980 it was this. Well, you know what? I can make my life a lot easier if instead of saying 1960, why don't I just call 1960 year zero? And we'll just pretend that that's when I start my clock. And so T will equal 0 in the year 1960. And so when I even begin to write this out, this is what it's going to look like. I'm going to say, okay, in year 0, here's 0, here's T. My population was 680,000. And so, okay, 680, and I'm not going to write the thousands, same way as before. Only in my head, I'm thinking, okay, 0, and I like to do this when I draw this so that I keep myself honest. I'm thinking, okay, that 0 is like unto 1960. So I'd like to have that there just to keep myself honest and say, yeah, okay, 0 is the year 1960. Okay, well, if that's the case, so I have one data point, and now my other data point is going to be in 1980. And so how many years is that? What would that correspond to here on the axis?
Sorry, 1 second. I'm still
Okay.
writing. Okay, so that's, oh boy. 1960 is 60, and then 19. Would that be, wait, what did you, I'm sorry, what did you ask me?
So we said, okay, we're gonna say that 1960 is year 0. And so 1980 would be year what?
2,
So
1. What?
So let's think about it this way. Here's and this is why I wanted to ask it that way, because this is how I think about it. We're basically taking these two numbers, 1960, 1980, and we're just dragging them to the left so that 1960 ends up at year 0. And if that's the case, what does 1980 end up at? That distance between them is still the same. We haven't changed that. And so what's the distance between these two numbers?
20.
It's still 20. And so if 1960 is at 0, 1980 is at what?
20.
20. There we go. And that's how I actually think about it, is I just think, okay, well, hold up. You have 1960 and 1980. And if I drag them back, well, the distance between them is going to stay the same. And if I'm dragging 1960 all the way down to 0, well, then 20, it's still 20 apart. And so 1980 would have to occur at year 20, or when T equals 20. And so now it's the case when I plug in a 20, I get out a 905. So it's the same picture we did before. The only difference is I just took this picture here and dragged everything to the left until my first data point went through here at what I'm calling year 0. And so the picture remains the same. It's still an exponential. It's still getting bigger. And so it does something like that. That looks like a line, and I'm sorry. That's just how I drew it. That's the idea. Okay, buddy. You got some crackers. Okay, so we're going to go through the same process here. Only this is going to be really nice in the first case. So I'm going to get rid of the old case here, the old thing that we did, and say, okay, I have 2 unknowns. I'm trying to find P0 and I'm trying to find K. And so I need 2 equations to do that. I happen to have 2 data points. And so I'm going to do the exact same thing as I did in the first case. I'm going to say when the input is 0, now my output is 680. And so here's my first equation. 680 equals P0 times e to the k times 0. It's my first equation. And this is the great thing about using 0. 0 is one of your best friends in mathematics because it makes life so much easier. What's k times 0?
0.
And so that means that we have 680 equals P naught times e to the 0. What is e to the 0?
0.
What?
Wait, e to the 0 is, oh, sorry, hold up. I'm still writing.
Okay.
P 1.
Yes, anything to the 0 is 1. And so 680 equals P0 times 1, or, oh, lo and behold, we already got our first unknown. Now the second data point, so okay, I'm gonna go ahead and move ahead. That second data point, I'm just gonna write it out as though I just did both of them to begin with without using my brain. It says that the output is 905 when, and then P0, e to the k, when the input is a 20. So k times 20 right there. But now, and this is the really nice thing, is, well, we already have what P0 is. We know that the initial value of the population was 680 or 680,000. And so why don't I go ahead and just substitute it in there? That'll get rid of it. Like if you really wanted to, you could do the divide the 2 things by each other and blah, 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 blah. But it's like, well, once you have one of the variables by itself, go ahead and plug it into the other equation. I'm sorry, once you have one of the constants, one of your unknowns by itself, go ahead and plug it into the other one. And so since we know that P0 is equal to 680, I'm going to just rewrite this guy as 905 equals, instead of P0, how about 680 e to the k times 20. Then we say, okay, I'm trying to get k by itself. We could just write at this point, take the natural log, but that's going to be unnecessarily complicated, right? Like we've done this kind of stuff before. We want to peel off as much as we can to get that exponent by itself. And so I'm going to divide both sides of this equation by 680. And I'm going to get 905 over 680 equals e to the k times 20. And you can see that this is much easier this way because we're almost done, right? Let me know when you get to this point. And if you have any questions along the way.
Alrighty.
Okay. So now that I have E by itself, I'm going to take the natural log of both sides of this. Natural log of 905 over 680 equals natural log of E to something. Natural log of E to something is just whatever that something is by definition. And so K times 20. I think we're about to hit the reason why they don't ask you to write the full equation, but rather they say solve for K, because it doesn't matter how tricky you are about this, K is always going to be, well, the same thing. It's one of the properties of this. So to get K by itself, this should look very familiar. In fact, we just did this. K is equal to natural log of that stuff, natural log of 905 over 680 divided by 20. And so we found K. We found P0. We could write our equation. P of T is equal to P0 is just 680. E to the KT, only K is, well, it's the same K we got before, natural log of 905 over 680 all over 20 times T, like that. Notice that the K is the same in both cases, but oh boy, that P0 is a lot easier to deal with. But here's the question. Now we're going to use this to estimate what the population is. Actually, let me know when you've caught up, when you got this written down.
Yeah, I'm good.
Okay, so here's the thing. And I want to keep this up here. Okay, so in your homework, I want you to draw every single time. I want you to draw this stuff out. And part of that reason is because of this right here. So we've drawn this out. I'm just redoing it to make it look nicer. That was 905. This was 680. Now, okay, it says to use your stuff to estimate the population in year 2015. So if that's the case, what do I need to plug in for T to be the year 2015? So 0 was 1960, and we said that 20 was 1980. And so then what value is going to correspond to 2015?
Um, $35.
35. So let's see. In 20, it's 1980. So 30 would be 1990. 35 would be 1995.
Oh, okay.
No.
I don't know.
Okay. The way I do it, the way I did it actually just a second ago in my head was I said, okay, if 1960 is 0, let's count by tens. 1960 to 70 to 80 to 90 to 2000 to 2010 would be 5. So 50 years to 2010. plus
Oh.
another 5 would be 55 years.
Oh, I was doing it from the wrong number. That's why. I
Cool.
kept.
And so,
Sorry.
yeah, 20, and then that is a distance of 35. Yeah.
Yeah, my bad.
Right. And so, and this is, I'm glad we had this because I was going to say this at the end. I'm just going to say this now. When you do this, when you've taken your information and you've shifted it some way, it's really helpful to say something like this. When you report this, you say where T equals number of years after 1960. So in other words, that's another way of saying 1960 equals 0, right? But this is in general how this is done in the world. We say number of years after whatever our 0 date is. Because if we just tried to plug, we're going to see this in just a second. So if I plug in a 55, I should get out the estimate of what the population is. So I'm going to do that on a calculator right now. All right. Hold this up. So, okay. The function says I take 680 and multiply it by, so I'm going to go 680 times e to some stuff. So second e raised to, okay, so I'm going to go natural log of stuff divided by something, and then I'm going to multiply that by t. I'm going to use parentheses to keep myself sane here. Parentheses, natural log of stuff, natural log of 905 over 680. And the natural log. Now I want to take that and divide it by 20. So I'm going to do that. So that was my k right there. That's what I did to find the k. Now I'm going to take k times, in our case, it's 55. And we get out 1492.43. So 1492.43. You have water, buddy. Where's your water? Okay. And so that doesn't mean 1,492 people. What does that mean in our context? Because 680 was what? 680 was actually what?
0.
It occurred at time 0, but we said it wasn't 680 people in Dallas. It was how many people?
680,000.
1,000 people. So 1492 is how many people? How about just throw on 3 zeros?
Mm-hmm.
Right? That's what it is. Like we said, so in order to get these numbers, we chopped off 3 zeros. So we'll just throw on 3 zeros right there. It would be 1,492,000, but I don't think about that. Like I just think, okay, throw on 3 zeros, then I'll figure out what it is. Okay, 3 zeros there, 3 zeros. Okay, so 1.4 million people. And there you go. That is that's the estimated population in 2015. Oh, I'm up in the corner, aren't I?
No, it's okay. I zoomed you.
Okay,
in.
you could see what I was doing. Okay, so, but I wanted to keep this up because I wanted to do this. Let's say that you're not using your brain, or rather, you're so sick of using your brain that you just say, okay, it says the population 2015. Okay, so T equals 2015. And so you do all this stuff and you plug it in just like we did before. And you go, okay, so 680 times e to the stuff to k, which is really ugly. And then I go times 2015, 2015. Let's see what we get. Okay, 2.18 times 10 to the 15. So I'm going to go 2.2 times 10 to the 15. And let's say that's what we ended up with. 2.2 times 10 to the 15. And so and I don't care how you answer this. If you say, okay, 2.2 times 10 to the 15 people, or if you go, oh, wait, you'll need 3 more zeros onto that. And so you go, okay, 2, so that's 15, that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then you go, oh, I need 3 more zeros. 1, 2, 3. So then your answer is 1, 2, 3, 4, 5, 6. So you say 2.2 billion people, not just 2.2 billion, but 2.2 billion. You should go, wait a second. Whoa. I messed something up here. And that's a major pitfall right there, because you can see how you just calculate it and then you answer 2.2 times 10 to the 18 and you're done. No, there's no city on earth that's going to fit that many people into it, right? So at the very end, we want to stop and kind of evaluate, okay, did all of this stuff make sense? And this actually makes sense. If you grow from 680,000 people to 900,000 people over the course of 20 years, give yourself another 35 years, it's perfectly plausible that you'll have 1.5 million people. That's plausible. I could see that happening. But to have 2 billion people, that ain't happening, right? So, okay. Any questions? We got one more topic to get into for your homework.
No.
Okay, so that is what we're looking for. This is what I'm going to want when they say solve for K. You get this. I want to know, because you're going to need to do it anyway, right? So you might as well, this is the thing that I'm looking for. And K, like, you'll be able to check in the back of the book if this is right or not. I want exact answers. They will probably have, yeah, they do. They've gone ahead and computed what this is. So if you would like to check your work, you could just figure out what that is by plugging it into a calculator and say, okay, in the back of the book, they say that K equals 1.072. You'll plug that into your calculator and you get 1.0719. You go, okay, yeah, I'm good. So that's nice. But this is what I'm looking for right here. One of these guys, every time they ask for that. And you're going to have to figure it out anyway in order to do the problem. So you might as well just make that your goal. And then estimate, right? Want to use our brains here. So, okay. The other thing is a half-life. That's what we need to talk about. So, okay. Radioactive elements decay. That means they spontaneously break down over time. Like uranium is one of them, and the atoms themselves break down and turn into something else. They're not stable. They split apart and turn into something that's not uranium. So turn into a lot of things. And so radioactive decay, it turns out it happens at a pretty regular interval. To be able to predict it exactly, like when's the next atom going to break, is impossible. Literally impossible because of problems with quantum mechanics that we can't get into. But we could say overall, it happens fairly regularly. And so, like I said before, if you start off with, say, 10 grams of uranium, you could predict how long it's going to take before that stuff, or how long it takes for that to decay. And so we model that with, lo and behold, the exact same equation. The only difference is this K value ends up being negative. And if you have e to some negative number times t, that thing, basically e has just been flipped around, right? It decreases as time goes on. That's not just e, I mean, that's any number. You have 3 to the negative 2t, that's going to look like that. It's going to keep getting smaller and smaller as time goes on. We've talked about that. If that's confusing to you, review stuff, but we need to get this done. So what happens is you have some initial value. We're going to call it P0. And over time, it decays. And it decays exponentially. That is, it obeys this kind of function. And be very careful with this. The half-life of a radioactive element is the amount of time. The amount of time. I'll say that again. The half-life is an amount of time. It's a measure of time. It's the amount of time it takes of a radioactive element, for a radioactive element to yeah, there's no better way of saying that. To decrease to 1/2 its initial amount. So we're thinking about this, right? As time goes on, we have less and less mass of, say, uranium. And at some point, as we can see, it's going to decay and just keep getting less and less and less forever. But if we think about this graphically, we could say, well, if you started at 10, then half of 10 would be 5. If you started at 20, half of 20 would be 10. Or if you started at P0, half of P0 would be, well, whatever P0 divided by 2 is. And so we have this going on here, this right here, this amount of time right here, that distance, this amount of time is what we call the half-life. I'm going to put it in H right there. This is, of course, the t-axis. Think about time goes on from the left to the right. And so the amount of time it takes for it to decrease from its initial value to 1/2 is the half-life. Okay. So here's how these are going to show up. We're going to do a few of these because they are very, very tricky. Yeah, let me go ahead and kick us off, and we'll meet up again in a minute. I don't want to get kicked off in the middle of what I'm talking about. So make sure you have all this down before I kill the feed.
Okay, hold on.
Okay. And that is an H. I've written it a big capital H right there. I'm going to do that again. Make that look more like an H. That isn't, almost looks worse. That's an H. It's the amount of time it takes.
I'm sorry, I'm having a hard time reading the.
Yeah, so the half-life of and I just abbreviating, a radioactive element is the amount of time it takes for it to decrease to 1/2 of its initial amount. And so, like I was saying, if you started with, say, 10 grams of uranium, it would take some amount of time for it to decrease to, say, 5 grams of uranium. The amount of time that it takes is what we call the half-life. You started with P0 grams of uranium, then the time that it takes for it to reach P0 over 2 grams of uranium would be H, the half-life of it. It's a terrible way of saying it, but this is the picture I have in my head right here. Something decays. Some amount of a radioactive element spontaneously starts decaying, and you have less and less of it left after a certain amount of time. The amount of time it takes for it to half, to become 1/2 of whatever you started with, that is what we call the half-life.
Okay.
And so it is a measure of time. It occurs on the t-axis. So that's the great way of thinking about it. This picture right here is probably the best way of thinking about it. So there's a lot of different ways that half-life can show up in questions. And here's one. And I'm going to, in every case, and this is for the entire homework, draw a picture, draw a picture, draw a picture. And so, for instance, we're going to do a couple of them. Number 24 on page 555. Number 24 says that the half-life of polonium, so the half-life of polonium, that's P0. No, that's the so we're gonna go polonium, the half-life of polonium-218 is 3 minutes. Okay, so they basically just given us a data point. They're saying that after 3 minutes goes by, whatever initial amount you started with will come down to 1/2. That's all they've said thus far. So now this is the question. After 30 minutes, after 30 minutes, how much of a 410 gram sample will remain? .410 gram sample will remain. Okay, so when I see something like this, what goes through my head is, well, they've given me it. Basically, they're saying we want something like this, so that when I plug in a 30, I'll get some number out. That's what they're asking. How much is going to remain? And this is the idea I have in my head. I want to get it so that I plug in a 30, and then this is the amount that they're asking for. This is what we want right here. This quantity right here. Now, what you could start doing is immediately going, okay, we know 410 is the initial amount, and so that's going to be my P0. We could do that, but the way I'm going to do this at first is to just find K. I want to get K. The reason why, and you'll see in just a second here, is like, what I could do is I could pretty much find this entire thing except for the P0 with just this information right here. All we need to know is the half-life. And that's how I'm going to think about it. So what I'm going to start off by doing is saying, wait a minute, they told me that the half-life of polonium is 3 minutes. So that means, and I'm basically going to draw this thing, I have some initial amount. It decays like this. And they told me that the half-life, in other words, the amount of time it takes for it to decrease by 1/2, right here, the half-life, that number is 3 minutes. And so I'm going to kind of think in my head, T is number of minutes. Now, notice, right, that's going to be important. Like if they told you 3 minutes and then they said after 60 seconds, how much, that's a different thing altogether, right? So it's going to be good to make sure that we know, okay, hold on. They give me information in minutes and they're asking for information in minutes. So I'm going to do my whole thing in minutes. I don't need to worry about that. So what I'm going to do is say, okay, this thing right here has this relationship. And this thing tells me that when I plug in a 3, I get out a P0 over 2. So I'm just going to go ahead and use that information right here. P0 equals K times T. So when 3 is the input, the output is P0 over 2. The whole idea now is to get K by itself, and it looks like P0, we could get rid of it. Let me know when you're up to here.
All right.
Okay, so I'm going to divide both sides of this equation by P0 in order to get 1/2 equal to E to the K times 3. And that's the cool thing about half-life, right? We didn't need to have 410 to start off with, because half-life means, well, whatever you started with, you just take half of that. If I tried to think about this as like, okay, well, if that's 410, then half of that would, well, half of 410 would be, I guess, 205. And so I'd have 205. And so we'd say, okay, when you plug in a 3, you get out a 205. And so you end up with the equation e to the k 3 equals 205. And then you go to solve for k, and you get 205 over 410 equals e to the k times 3. 205 over 410. Oh, yeah. That's how we got it, right? Like half of that, yes, of course, it's going to come out to be a half. Okay, so now in order to get k by itself, I'm going to take a log of both sides. Natural log would be really nice. So natural log of 1/2 equals natural log of e to, well, whatever that is, just pops right out. And so k times 3 is equal to natural log of 1/2. So k equals what?
Natural log of 1/2 over 3.
There you go. Natural log 1/2 divided by 3. There's k. Turns out to be a negative number. If you want, you could plug in natural log of 1/2. You get negative 0.69 something, I think. And so yes, that is a negative number. So that agrees with the fact that this thing is decaying. And so we got that. Okay, so that's nice. I got one of my unknowns. I'm going to plug it in right here and say, all right. Another thing, so now I'm kind of thinking about the bigger picture now. They're saying after 30 minutes, how much from that much will remain? Well, if that's my initial amount, then 410 is my P0. So I'm going to go ahead and write that there and say, okay, the P of T is equal to 410 times E. You're okay, buddy. You're all right. Natural log of 1/2 over 3 times T right there. Hey. Oh, no, you got the And now they want to know, okay, all right. Oh, yeah, I know you're not feeling so hot. It's okay. So now we want to know, they're asking us after 30 minutes, how much remains. And I'm just double checking that, yeah, everything I've done so far has been where T is equal to minutes. And so 30 minutes, I don't need to worry about that. I could just say, yes, that is what's going on. So I'm going to plug in a 30. And I should get out the amount that we want right here into that equation. And let's see what happens when we do that. P of 30 is 410 e to the log 1/2 over 3 times 30. And I'm going to do that in the calculator right now. All right, love you. So let's do that in the calculator. So 410 times E to the natural log of 1/2. And I'm going to use parentheses again to get my entire K in one thing. Natural log of 1 over 2 times or divided by 3. That's my K value. I put parentheses around my K, and now I'm going to go times 30. And I'm expecting it to be, it had better be less than half. It had better be less than 205. So let's see. It should probably be a lot less than 205. Yes. 0.04004. So, oh, you didn't see, I didn't share that, did I? I'm just sitting here like, okay, and then it's this and that, and yeah. Okay, so actually, I'll share that real quick just so you can see the calculations that I did. So that's what I did. I said 410 E, and I put parentheses around the K part. So you get that log 1/2 divided by 3. Then I took that and multiplied it by 30, and I got 0.400, round it to 4 is good. And that is grams. That is how many grams of polonium should remain after 30 minutes. So if I started with 410 grams of polonium after 30 minutes, I'd have 0.4. So that's what that means. Okay, so that's one way that half-life we could use half-life. Another way is I'll say a certain radioactive substance decays from a certain amount to a certain amount in a certain amount of time. What's its half-life? So let's do that. Can I get rid of this stuff up here?
Yeah.
Okay, so notice I'm keeping this same equation up there the whole time. I'm keeping that function there because everything is going to come down to this function. It's just a matter of, is K negative? Is it positive? If it's negative, it's decay. If it's positive, it's growth. But it's all modeled with the same thing. So this is number 26. Some substance, some substance decays from 66,560 grams to 6.5 grams in 16 days. What's the half-life? Okay. So again, I'm always going to start with a picture. Tells me that we're going from here to there. So I know that's decay, and they're talking about half-life, so it's got to be decay. So I'm imagining, okay, why make it hard on myself? Let's take my first data point to be here at 0. And so we start here at 66,560, 66,560, and we end up down here at 6.5. 6.5. And we want to know the half-life. That is the bit that we're trying to find out, is the half-life. Oh, and we also know that it takes a total of 16 days for that to happen. So there's my time. I'm looking for a function that's of this form right here, that when I plug in a 16, I get out a 6.5. When I plug in a 0, I get out, oh, that one's easy. That one's real easy. I'm going to start there and say, this tells me that when I plug in a 0 for this, P of 0, I get 66,560. But when I do that, I get e to the 0, which is just my initial value. This is why in the formula we call it P0, because when you plug in a 0 right here, that's the value you get. That's the output, the initial population. Okay, so we have that. That's easy enough. I'm going to go ahead, just like last time, plug that back into my original equation, 560 e to the k times t. And now the only other data point that they give us, can I erase this stuff? You got your P0?
One sec. Yeah, I'm good.
Okay, so that's how we got P0. And now they tell us that when we plug in a 16, my output is 6.5. So I'm going to take my function, plug in a 16, so that's k times 16, and my output should be a 6.5. Only thing I need to do is find k. Yeah, and then I'll have my function, and I should be able to answer any question they throw my way. And so I'm going to divide both sides by 66560. Then I'm going to take the natural log of both sides. And I'm going to finish this up over here so that the natural log of 6.5, 66560 is equal to k times 16. So that k is equal. And this is, you could see, the same game as we played pretty much all day. There's my k. I have my P0. I have my k. I should be able to answer any question that they want. So now that I have both of those, I'm going to rewrite my formula. 66560 e to the that stuff, log 6.5, natural log 6.5 over 66560 over 16 times t. That is the thing I want. Now they want me to find the half-life. The half-life is the amount of time. So I know that I'm going to be solving for t. That's the idea, that there's some number t that lives here, so that when I plug in that number, I get out 1/2 of the original. Now I could, if I were so inclined, take 66560 and divide it by 2 and find out what that actual number is. Or I could be a little tricky here and just say, well, whatever half of it is, it looks like that. It's that number divided by 2. And in other words, we're trying to find this value here, whatever that is. When I plug that in, I get out that number right there. Can I erase this stuff now?
Yeah.
Yeah, all I did was solve for k, right? And you're going to notice something here. So we're trying to find the value of t such that when I plug it into this original equation, log of 6.5 over 66560 all over 16 times t, what value of t makes it so that we get out 66560 over 2. No, not yet, buddy. Where's your, what happened to your crackers? Here, where's my crackers? And the nice thing is the same way that we did this earlier, where we didn't have to use our brains, we just divided both, here, buddy. We just divided both sides by P0. Well, that's technically what I'm going to do right now. I divide both sides by, well, P0, and I should end up with 1/2. Yeah, right? E to the natural log of stuff. I'm not going to write all that down. Natural log of stuff over 16 times t. Take the natural log of both sides, and I get natural log of 1/2. That looks familiar. Natural log of all this stuff, log over 16 times t. That makes that stuff pop out. And so I have the natural log of 1/2 is equal to natural log of all that stuff over 16 times t. And so that t that I'm looking for the half-life. Oh, I have a fraction. I could multiply both sides by 16 and then divide both sides by that log. And what's that going to look like? Well, how about 16 times log 1/2 divided by log of that ugly stuff. It's t. And log of that stuff, I stopped writing it a while ago. It was 6.5 divided by 66560. And I like to do that. T sub h. Like that's basically what I did. I could have just used h, but what I was saying was there's some special time. We'll call it T subscript h because it's special. And when I plug it in, I get out 1/2 of what I started with. And that's what we did here. He said, plug in T sub h right there. And this is what you get, blah, 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 blah. Finally, solve for that. So if they're asking you what the half-life is, well, half-life is a amount of time. It should be some amount of time. You should be solving for t. That's the idea here. If they give you a half-life, well, that's a way that you could use to kind of pull this thing apart and find the different values and stuff like that. But in this case, they wanted to know, what is the half-life? Well, the half-life is a time. The half-life is an input. The half-life lives right here on the t-axis or the input axis. So it makes sense that I'm going to have to solve for whatever that input is. And that's what I did. And if you want, plug that into a calculator. This is an exact answer right there. That's a better answer. But if you wanted to estimate it or check your work in the back of the book, plug that into a calculator, figure out what that stuff is. That's the idea. Any questions?
No.
No? Okay. And so we're not going to go over other examples, although there are a few other ways, because you can imagine, right? There's two constants. There's also two variables. There are a bunch of different ways that they could give you enough information to solve a question. But, you know, there are 4 different, so 4 choose 3, whatever that is. Like there are a bunch of different ways that they could leave one of those bits out and ask you about it, right? And so we've talked about 2 ways, but I think that in every case of everything that's in your homework, if you start with a picture, it makes your life a lot easier, right? Like in this case, they ask what's the half-life, so I know that I'm looking for a value right here. In the last case, they gave me these 2 values, right? And I knew that they were at, or they gave me the half-life, and they wanted to know what is this output value here. And so, at least for me, having a picture to organize all of that takes a lot of the guesswork out. So if the thing that they're looking for is an output, I know that I need to find some number to plug in and give me an output. In this case, they're asking, what is the input? What is the half-life? I know that I'm going to be solving for an input value right there. And so that will help guide you through all of this. So homework. I think that should be it. There's nothing else tricky there. And we won't do that one. No, I was going to get that one. Okay. Can I erase this stuff?
Yep.
Okay, so I'll just put the homework right up here. And this will be due in a week. So you got some time. Are you still there? Oh, yeah, you dropped off for a second. This will be due on Wednesday, next Wednesday. So you have a full week for this. I think it only works out to like 13 problems or something like that anyway. So it's no big deal. This is chapter 12, section 8. Yeah, 8 on page 555. 6. We did not talk about 1 through 5 odd. you are more than well, it's just graphing different functions. You are more than welcome to use Desmos or whatever you want. I would suggest, though, try to get it without Desmos first.
Okay.
So for instance, here's one. It'll say graph this, y equals, here's one that you don't have, 2 times 1 minus e to the negative x. What I would do is start with, well, I know what e to the x looks like. I start with the innermost thing. Look at what happens to x and then start working your way out. And I could say, well, if e to the x looks like this, then e to the negative x looks like that. So then minus this would flip it down like that. This would be minus e to the negative x. I'm just going to keep working like that and say, okay, now you're adding 1 to that value. So that should bring everybody up by 1. And so maybe it looks something like this. I probably have that wrong. This would be 1 minus e to the negative x. Then I multiply it by 2. And so it stretches everybody out more like this. And so I go 2, 1 minus e. This is like the hardest one on the page, by the way. They're much more straightforward. But I would try to do that kind of thing first, and then go ahead and graph it with a graphing calculator on Desmos and just try to piece that together, you know. But really what I want you to take from it is that just try. That's all.
Okay.
Just try it. Just give it a college try. So then there's a bunch of stuff I don't want you to do because it's literally plug in a number into a calculator and you're going to get plenty of that with this homework. So we're not going to do that. We're going to jump to 23. 23 through 30, 5, 6, 7 through 37 odd. You've already done 39, and that's enough. That's fine. You don't need to do those others. So that'll be it right there. It's actually not that bad. So